In the final video of today's lecture, let us solve a little bit more complex problem. So in this problem, at a first glance, you might think that this can be, simpler than previous problem, because in previous problem, we have the loading for the entire domain, but in this example problem, we have loading just one point, and at a first glance, you might, it's okay to think that this is simpler problem. However, the problem is, at least for this guy, we're gonna have a piecewise mx function. Okay, so because when you convert this into statics problem, so from the statics, you're gonna obtain fa and fb. So you're gonna quantify fa as 3/4p, fb as 1/4p. From the simple torque and force equilibrium. Then the problem is mx is now a piecewise function, and how many pieces do you expect? For this problem, when you have a concentrated load, or similar problem when you have concentrated moment, you're gonna have 1 and 2 section. Here you're gonna have 1 and 2 section. If you have like a 2 concentrated loading, if you have a 1 external force and 1 external concentrated moment, you're gonna have 1, 2, 3 piecewise mx. Or if you have a problem with distributed loading in one region and no loading in the other region, you're gonna have expression for mx here and the other expression for mx here. You're gonna have like a two analytical expression in two domains, okay, in the beginning or end of the distributed loading. Okay, so when this problem happens, you gotta need one more boundary condition, and this example problem is about how to utilize that boundary condition. So as I told you, because this guy has one concentrated loading, you can consider two pieces, first piece and second piece, and to get the two analytical expression, let's take two imaginary surface A and B. So let's consider cut A, where x is larger than 0, smaller or equal to 1/4L. P is located at x equal L/4. Okay, so if you draw free body diagram, I will not gonna go to the details about this free body diagram, because we have done this example and practice a lot in previous chapters, chapter 5 and chapter 4. So V turns out to be 3/4p, and M turns out to be simple linear expression 3/4px. Now when you consider cut B, okay, and try to have free body diagram of this entire left region, so we have 1 and 2 external loading, and regarding the interface reaction, shear force and moment, out of the force equilibrium, B turns out to be a negative 1/4p, and out of the moment equilibrium around this point, and if you take counterclockwise as positive sign of this moment, and summation of this moment should be 0. So there is a local moment mx, there is a moment due to p times x minus 1/4L. This is x minus 1/4L, and you have minus 3/4p times x. The length is x, and 3/4p gives like a clockwise moment, and you have three cause of the local moment with respect to this green point, and you have another expression about m. So mx expression is quite complex. Okay, so when x is smaller than L/4, we have a simple linear equation. When x is larger than L/4, we have a little bit more complex equation, like a linear term plus some constant term, right? So given these two piecewise expression for m, so let's try to go third step, integrate twice. So if you integrate first time and second time, you're gonna have expression, two different analytical expression in two different region. First section and second section, you're gonna have this expression and that expression, and each section you're gonna have integration constant C1 and C2 and C3 and C4. So you have 4 unknowns now. Okay, which means that to solve this equation you need 4 boundary condition information. Okay, so let's try to apply boundary conditions. So the first boundary condition you can utilize is ya equals to b0, and second one is yb equals to b0. Okay, so A point, this is simple supported beam. B point, this is also simple supported beam. So you can use ya should be 0 and yb should be 0, which means that y x equals 0 is 0, y x equal L should be 0. Okay, so these are the the 2 boundary conditions that you can immediately come up with. And then you can consider third boundary condition, because you are considering a beam deflection. You don't consider beam breakage and beam disconnection. Okay, so even though we have 2 different expressions for first and second region, beam does not break. It's not broken. So y left and y right should be same at x equal 1/4 L point. This is x equal 1/4 L point. Even though the analytical expression for left side and right side are different, to make this problem physically correct, you have to have same y at x equal 1/4 L. Okay, so that's the third expression, third boundary condition you can use. And we can have another boundary condition. In addition to the absolute value of y, we should also have the first derivative dy dx should be same at left and right at x equal L/4. Even though we don't have same expression for left and right side, they should have the same first derivative, because if this condition violates, if they are not equal to each other, then you can immediately see that due to the by the definition, the second order derivative will be infinite. If the second order derivative is infinite, second order derivative and the local moment is proportional to each other, it means that m is infinite. However, there is no way that local moment becomes infinite at this point. Okay, so because local moment is not infinite, this condition should be satisfied. So I told you that there is 4 unknowns, but we can find 4 equations, 4 linear equations, and we are guaranteed to solve this equation and this linear differential equation. Okay, so here's how to apply the equation. From ya equals to b0, you plug in y x equal 0 point should be 0, so you can obtain the c2 equals to b0 out of this equation. Then out of yb equals to b0, you plug in x equal L and then y must be 0. So from these equation, when you plug in x equal L, and x equal L, this must be 0. And this gives us one more information about relationship between C3 and C4. Now regarding y left and y right equals to be each other at x equal L/4, you plug in L/4 here, L/4 here, and then they must be equal to each other. Okay, so this gives us third equation. Then you can do a first order derivative, or you already have first order derivative here and there, and after considering this first order derivative and plug in x equal 1/4 L, they must be equal to each other at this point. Okay, then we're gonna have fourth relationship. So given 4 unknowns and 1, 2, 3 and 4 relationship, you are guaranteed to find and solve C1, C2, C3 and C4. Okay, so this is how to handle a problem where you have to have a piecewise function for mx. Okay, so with this let me finish today's lecture, and I will move on to the contents of beam deflection in next lecture.